Endochondral ossification is a very complex process compared to intramembranous ossification. Endochondral ossification, it introduces us to a lot of new vocabulary. So similar to intramembranous ossification, we have to start out with a model of the bone. However, instead of this being a sheet of dense connective tissue, the model for a long bone is a hyaline cartilage model made by those cartilage cells called chondrocytes. And let me draw a few of them in here, right? So we have a few chondrocytes that are in here making this hyaline cartilage model. Because cartilage is not vascularized, the chondrocytes at the center of the model get cut off from oxygen and glucose as they make the model bigger and bigger. So they begin to die, and they basically leave their lacunae, or their holes, empty. And this results in a whole bunch of tiny little holes in the cartilage model. So osteoblasts that are living at the outer edge of the bone, right, because they are in the periosteum that you can see here is starting to form. Osteoblasts start to replace this hyaline cartilage model with bone. They start to secrete the bone against the outer face in appositional growth. And this forms that bone collar, which is that layer of compact bone along the outer edge of almost all the bones of your body. And this collar provides support to the elongating bone. And we've discussed how this bone collar is very much like the starched collar of a shirt. The osteoblasts at the edges, they start to form that complete inner layer, that complete cellular inner layer of the periosteum, and this separates the hyaline cartilage model from any of the tissue surrounding it. So this is like the first moment that it's an organ. As all this is happening, blood vessels are coming very, very close to the periosteum and even perforating the periosteum in places, right? Those nutrient foramina, which are the holes that the blood vessels can perforate. When the blood vessels finally vascularize the center of the diaphysis, we have our first ossification center, and that's what this is. It is the primary 1' ossification, and I'm just going to abbreviate that because it's typed up there. Ossification center. At this ossification center, osteoblasts, fully fed by blood vessels, are secreting osteoid, and the matrix of the bone is becoming mineralized with calcium. Slowly, the osteoblasts in the primary ossification center replace the cartilage of the diaphysis with bone. And this primary ossification center will ultimately be dug out by osteoclasts and turn into the medullary cavity, which will then fill in with adipose connective tissue of bone marrow. As the medullary cavity starts to form by the action of osteoclasts, the bone becomes more and more vascularized with those perforating canals that run transverse to the periosteum, and then those central canals that are at the center of each osteon running parallel with the periosteum. An area referred to as the metaphysis. And there's two metaphyses. There's a proximal and distal here. These areas start to form, and this is an area where chondrocytes still remain after birth, and they're creating cartilage via appositional growth at the edge of the bone. As they create more cartilage on the border of the diaphysis and the epiphysis, the developing epiphysis is pushed away from the diaphysis, elongating the bone. And these things called spicules, which we'll see in the next slide, there's something like stalactites or stalagmites of caverns and caves. These spicules, they stick out into the medullary cavity of the diaphysis. And it's here that the osteoblasts are turning newly formed cartilage into bone tissue. So as these chondrocytes are pushing themselves away from the diaphysis, the osteoblasts are like chasing them, and they're following them, laying down bone to replace the hyaline cartilage. The final steps of ossification occur with even more vascularization of the bone. And this time, these are called secondary ossification centers, and they're located in the proximal and distal epiphyses. So this is a secondary ossification center. This is a secondary ossification center. I feel like this last diagram here, it like skips a bunch of steps between the one previous to it and here, right? There's a lot of structures there. There's osteons, marrow, ossification centers, periosteum. But to form these centers, the secondary ossification centers, chondrocytes have to die. And then osteoblasts have to, again, replace the hyaline cartilage with bone. And it's then that the osteoclasts will then come in and help to create the spongy bone and the ossification centers. Activity at the metaphysis continues after birth. And this ever-expanding region is called the epiphyseal plate or growth plates. While the chondrocytes are still active, pushing themselves away from the diaphysis to elongate the bone, these plates are referred to as open or active, or just called plates. And this means that the bones, they are still growing, they are still elongating. This histological inset here, it's actually really good, but it can be hard to understand. But what it's showing you here is the epiphyseal plate. At the top of the slide, or at the top of the picture, you can see the chondrocytes and the cartilage. That blue swath there is a bunch of chondrocytes. This blue swath is a bunch of chondrocytes doing mitosis and replicating themselves. Mitosis is happening to the chondrocytes in the lacuna, and the new cartilage is being built in this zone. But that blue swath, it never actually gets bigger because the chondrocytes at the bottom of this blue swath down here, they're dying. And this white area here in the histological picture is the area of the dying chondrocytes. As this happens, osteoblasts are moving upward, right? There's our bone tissue there. So these osteoblasts are moving upward and replacing the newly formed and newly dead cartilage with bone. I once heard someone, or maybe I read it somewhere, I can't recall these days, but I once heard someone say something like the osteoblasts chase the chondrocytes, pushing the epiphysis away from the diaphysis. I kind of like that because those chondrocytes, what they're doing is the appositional growth, but only on the inferior edge. And every time they replicate themselves, they push themselves more and more superior, right? They keep pushing and pushing. Then the osteoblasts, they ossify the dead remains of the cartilage and follow those chondrocytes as they move superiorly. When the chondrocyte activity has permanently ceased at the epiphyseal plate, and the osteoblasts they're no longer replacing the newly formed cartilage with bone tissue, the epiphyseal plate becomes an epiphyseal line. And this means that growth, it has ceased, and that there is no longer any activity to elongate the bone. This is what is called closing of the plate, or morphing the plate into a line. And it's usually influenced by a big push of estrogen and testosterone in puberty. You can see epiphyseal plates along long bones in x-rays. When we talk about a long bone, we tend to think about like the femur or the humerus, but your metacarpals and metatarsals and all of your phalanges are long bones too. The open epiphyseal plates, they almost look like open spaces on an x-ray, as though the epiphyses of the bones are not even connected to the diaphyses. But once the plate closes, the epiphyseal line is made of all bone, all compact bone, and there is no space. So this is why we call open plates to denote growth and closed plates to indicate that growth has ceased.